Dear friends, welcome to this lecture of inner product spaces. In this lecture, we shall see how a vector space can be expressed as direct sum of its a subspace, direct sum of a subspace and its orthogonal complement. So, I have written the result here, which is theorem 3. The theorem 3 statement is if V is finite dimensional inner product space and if W is subspace of V is a inner product space, W is its subspace, then this V is expressed as direct sum of W and orthogonal complement of W, or more particularly or more precise, this can be written as V is direct sum of W and its orthogonal complement. So, now we shall see what is the meaning of direct sum and orthogonal complement. So, if V is, see, this is defined earlier, direct sum. If V is a vector space and see this is a vector space and if U1 etc. UN are subspaces of V, then any element of V, if or we can say V is direct sum, then V is direct sum or internal direct sum of U1 up to UN if every element V belongs to V can be expressed uniquely as V is equal to U1 plus up to UN, where UI belongs to UI, I takes value 1 to N. So, this is the meaning of direct sum, and see if this U1, U2, UN are subspaces of V, and we can express every element of V as sum of the elements from these U1, U2, UN, and this expression is unique. Then we say V is direct sum of these subspaces, and we can write V as U1 plus etc., and we write this as U1 direct sum etc., direct sum up to UN, because element of V is expressed in this form U1 plus U2 plus up to UN, where U1 belongs to UN etc. So, this is the meaning of direct sum. And what is the meaning of orthogonal complement? See, again, if W is a subspace of a inner product space V, then we have by definition orthogonal complement of W is X belongs to V, those elements in the vector space whose inner product with an element in W is equal to 0. This is for all W belongs to W. This is the meaning of orthogonal complement of W. Now, we shall prove the result. See, V is finite dimensional inner product space and we have W is a subspace of V. W will be also inner product space because V is inner product space and W is subspace of V. Since W is a subspace of an inner product space, W itself is a subspace. W itself is a inner product space, is an inner product space with the product, inner product defined in V. The same inner product defined in V will be for W, restricted to elements in W. W itself is an inner product space, and because W is an inner product space by theorem 2, that is a Gram-Schmidt's orthogonalization process, we can find an orthonormal basis of W. So, this is by theorem 2, W has an orthonormal basis. Orthonormal set, and suppose the set is we will denote W up to WR. We are assuming the dimension of W as R. So, W has an orthonormal set as its basis. So, this is basis of W. Now, we shall suppose let V belongs to V, vector space. Then this we can write by earlier lemma number 5. Then by lemma 5, if V belongs to V, we can write. So, we have the expression for V can be written as see, we have V naught. V and V naught both belongs to V. We have V naught is equal to V minus inner product of V and W1 with multiplied by W1. V minus inner product of V and W1 multiplied by W1 minus inner product of V and W2 multiplied by W2 minus and so on. Inner product of V and WR multiplied by WR. So, this is the expression for V. If V belongs to V and we have V naught, we have this V naught is orthogonal to each of W1 up to WR. We have V naught is equal to this, is orthogonal to each of W1 up to WR, and thus because this V naught is orthogonal to each of W1 up to WR, V naught belongs to the orthogonal complement of W. V naught belongs to orthogonal complement of W, and thus V naught belongs to orthogonal complement of W by definition. So, when we say V naught is in this orthogonal complement of W, if the product of V naught with each of W belongs to W is 0, and this is orthogonal means the product of V naught with W1 is 0, the product of inner product of V naught with W2 and so on is 0. So, therefore, this V naught is in the set that is orthogonal complement of W. And further also we can write now V can be written as now. So, we have then this is V naught and is orthogonal to each of this. So, now what will be expression for V? We have expressed any vector V naught like this, and that vector becomes orthogonal to each of these W1, W2 up to WR. Now, we can write V as shifting these all negative terms on this side, and V will be V naught plus inner product of V with W1 multiplied by W1 plus etc. plus inner product of V, I shall write here, plus inner product of V with WR multiplied by WR. Now, you see here V naught is in orthogonal complement of W, and what is the remaining? If you make two parts of this, then this is linear combination of W1, W2 up to WR. That means it is a linear span of W1, W2 up to WR, and therefore it belongs to W, because this is basis. W1, W2, WR is basis of W, and therefore the linear combination of these W1 to WR must belong to W, and this belongs to orthogonal complement of W. Therefore, V belongs to orthogonal complement. This belongs to orthogonal complement and this part belongs to W. So, V belongs to orthogonal complement of W plus W, and that means or that is, or this we can write V, yes, this is the vector V, and this expression is unique, and therefore we have V, or this can be written as this happens for every V. So, this is true for every V, for all V belongs to V, and thus V is, therefore V is equal to orthogonal complement of W plus W, or this V is equal to W plus orthogonal complement of W, and this expression is unique. This expression for V is unique, and therefore we say V is direct sum of W and W1, and thus this expression of V is unique, and therefore this proves the theorem V is direct sum of, thus V is direct sum of W and orthogonal complement of W. So, this proves the theorem. So, this proves, this completes the proof. Now, we shall consider one corollary, and that corollary is for this theorem. So, the statement of the corollary is, the first part is the same, that if V is finite dimensional vector space, inner product space, and if W is subspace of V, then we have double orthogonal complement of W is equal to W. Double orthogonal complement of W is equal to W. Orthogonal, that we have defined earlier and can be considered as geometrically as perpendicular. Orthogonal means perpendicular. So, double perpendicular of this space or a vector will be the same vector, and we shall prove it. Now, first let W belongs to W. Then we can write as this, if inner product of W with U is 0, then that U is in orthogonal complement of W. If U belongs to orthogonal complement of W, then we have X U or W and U, inner product of W and U is equal to 0. See, if U is in the orthogonal complement of W, then its inner product with W is equal to 0, and this happens for all U, and that means W is in orthogonal complement of W. So, this implies W belongs to the orthogonal complement. See, U is in orthogonal complement of W, and the inner product of U and W is 0, means W will be in the orthogonal complement of W. So, that means see, we have W belongs to W, and we have here W belongs to double orthogonal complement of W. That means this first set is subset of this one. So, therefore, thus W is subset of the orthogonal complement of double orthogonal complement of W. Now, we have by theorem 3 earlier we have proved, here it is, V is, by theorem 3 we have V is W plus orthogonal complement of W. This can also be written as, also V is equal to, in place of W I shall write the orthogonal complement of W. So that means a vector space is direct sum of a subspace plus its orthogonal complement. And if this is the subspace plus its orthogonal complement, I shall write this. In place of W, I have written orthogonal complement, and therefore we have to write again its orthogonal complement. And thus V has these two expressions, and these sums are direct. We have proved earlier this V is direct sum of this. So both the sums are direct. Since these sums are direct, we have you can see this can be interchanged, and we can write the dimension of W is equal to dimension of orthogonal complement of W. So we have this can be interchanged, or we can write like this: double conjugate, that is double orthogonal complement of W plus orthogonal complement of W. Now these two dimensions are equal. So we have dimension of W is equal to dimension of double orthogonal complement of W. And also we have earlier here W is subset of this. Also we have W is subset of double orthogonal complement. So that means this is a subspace, W is subspace of double orthogonal complement, and their dimensions are equal. So this shows that, or this implies, both must be equal. So this together implies, this implies W is equal to double orthogonal complement of W, and this proves the corollary. So thus we have shown earlier a vector space is expressed in the form of subspace plus its orthogonal complement, and we have shown in this corollary as double orthogonal complement of W is equal to W. So now one simple example I shall state here is for inner product. So we will have this example, or not only inner, yes, in inner product, V is inner product, or in any inner product. V belongs to V, prove that norm of U plus V whole square plus norm of U minus V whole square is equal to twice into bracket norm U square plus norm V square. Now this result is simple to prove. We can consider with the LHS. The LHS is norm of U plus V whole square plus norm of U minus V whole square. And norm, by definition we know, inner product of norm square is inner product of the vector with itself, and that means this is U plus V, inner product of U plus V with U plus V, plus inner product of U minus V with U minus V. And this can be expanded using the linearity property, or we have proved this as lemma 1. Using this lemma 1, it can be written as, so we can express this as inner product of U and U plus inner product of U and V plus inner product of V and U plus inner product of V and V. That is the first expression. See, actually we have this alpha U plus beta V and alpha U plus beta V, inner product of this alpha bar, inner product of U and U, plus here alpha beta both are 1. In the second inner product, beta is minus 1. So, that is the difference. And because these are 1 or minus 1, their conjugates are the same, and therefore, there is no need to consider these conjugates. So, it will be alpha, alpha bar, alpha, beta bar, u, v. With this result, lemma 1 we have proved, you can refer that, and plus alpha bar beta, v u, plus beta beta bar, v, inner product of v and v. So, this is the result we are using, and plus now what is the second part, inner product of u with u plus that will be minus inner product of u with v, minus inner product of u with v, then again it is minus inner product of v with u, and last is negative of a negative, that is positive inner product of v with v. And you see these two terms cancel, and what we get is double term of this is equal to twice inner product of u with u, and the last is again plus twice inner product of v with v, or that is 2, and this is norm u square and this is norm v square, and 2 can be taken common, and this proves the result. And this is the RHS. So, this proves the result. So, in this lecture actually we have proved this theorem. Any vector space can be written as direct sum of a subspace and its orthogonal complement. So, thank you for watching the lecture.